You can hear me? Am I audible, Umar? Okay, perfect. So how are you? How's everything?
Alhamdulillah, sir, I'm fine.
Yeah, great, Alhamdulillah. So is this timing suitable for you?
Yes, sir.
Okay, perfect. So do you remember last time what we were doing? We were in the middle of gravitational fields, right? We had started gravitation, and um, we discussed gravity and even the expression for which is the universal law of gravitation. We discussed that as well.
Yes, sir.
Right. Okay, good. So do you have any questions from the previous classes?
No, sir.
Okay. So we have Hasib over here as well. Hasib, this is your first class? Right. So I'll just quickly introduce myself. My name is Basil Abdul Majid. I'll be teaching you A2 level physics, and I'm a graduate from NUST, and I have been also recently working actively in the physics department at NUST as a graduate teaching assistant. And so far we have started with the course already, and you can say that the first week was kind of a demo class week, where we did things at relatively slower pace as well. If it's if everyone is okay with the understanding, or you can also say if you say that I should increase the speed, so I'll gauge my speed according to your opinion of the class, right? So the lectures have been recorded, and the first week lectures, the demo class lectures, are also available on YouTube. I'm sure that all of those lectures have been uploaded on YouTube. So you can go and have a look at those, and so you can get an idea of what we have done so far. We have completed circular motion, and we are almost in the middle of gravitational fields. So Hasib, do you have any question so far regarding to whatever I just said? Until then, I'll share my screen. Need to. Hasib, do you have any question? Okay. Hasib, also okay, perfect. So let me know that if this timing is suitable for you as well. And so, okay, it's fine. Perfect. Right. So we'll continue from what we were doing. I'll just quickly revise everything that we did so far in gravitational fields. So we started off with the idea of gravity. And well, because I even work in the domain of general relativity and quantum field theory, so I thought that it would be interesting to start off with the idea of space-time curvature and the real geometrical nature of gravity. So that's what we did. It's not really a part of your course. So I would rather also say you did not miss a lot of what we have been doing. And so we talked about fields. Mathematically, fields are defined as this plus, minus, multiplication, division, a set of these operations which act on real numbers, which just means that there is a field of real numbers where you can do these operations with those real numbers. So you can 1 plus 1, you can do this, which is 2. You can minus 1 from this, which is back 1. You can multiply this with 2, which would give you 2. Then you can divide it by 1, which would give you back 1. So these are just set of operations: plus, minus, multiplication, and division. In physics, for us, it's enough to say that a field is something which will take values at each point in space. An example is a temperature field, where I gave an example. If you're standing in a room and there's a fireplace in the room and a window, you can measure temperature at every point in this room and get a value for it. So near the fireplace, the value would be higher, which means the temperature is higher at that point, or near the window where the temperature would be low. And so you would get a lower value for temperature at this point. But at every point, you will have a value of temperature. So that's the idea of a field. Now, how do I relate this to gravitational fields? Gravitational field is also a field in space-time. Well, we'll just consider space for our purposes. So it's a field in space where if I have any object of mass m, it creates a field around that mass m. So I have to put this mass in the space and it creates a field. Now, Newton himself did not know what is the source of this gravitational field. So he said in his book in Principia that this is left as an exercise to the reader. And so it took Albert Einstein to figure that out. And Einstein said that the source of gravity is the space-time itself. Right? So he combines space and time. And I'll also give you a very quick example why space and time, it might seem that it's a weird thing, but it's not. You use it in your normal daily life as well. So for example, consider that you were to meet a friend. You would call him and you would tell him that let's meet at this particular restaurant. And if you only say that, then there is no communication of at what time are you going to meet this friend, right? So you have basically specified the space part, which is the location where you're going to meet. So spatially, this person knows that you're going to meet at this restaurant, but he does not know the time, and so he does not have the complete information to successfully meet you. So you need to specify both location and the time. Hence, we say space and time are connected. So this was just one of the examples. We use it in our daily lives, and it makes the idea of space-time a bit intuitive. So that's a space-time. I'm just revising things, so that's why I'm going a bit fast. All of this is available in the lectures that have been shared on YouTube as well. The previous lectures that you new people in this class might have missed. So that's the idea of gravitational field. So we'll not be concerned with space-time. We'll just say that when you put a mass in your space, it creates a gravitational field around that mass. But I just told you the reason, the real reason for that field to be created in the first place. Now, if I bring any other mass, let's say you have a sun, and you bring small masses, let's say Earth is very small compared to the sun, and you put it in this near the sun. Now, as long as this Earth is in the gravitational field of the sun, there will be one sweet spot, which would be the radius from the sun of the Earth, where the Earth starts orbiting the sun. If the value of radius is that particular value, I'm calling that a sweet spot, as in it would be the optimal radius for the Earth to move in orbit of the sun. So that's why planets really orbit a massive star or even a massive planet. And similarly, we have Moon, which orbits the Earth. Now, these planets are constantly falling towards the Sun as well. And so to explain that, we'll have to go into much more detail, which I'll just quickly try to show you what really happens. What is really happening is that the solar system is not a stationary kind of thing. It's dynamical, it's evolving, you can say. So for example, the sun, it's not stationary, it's not sitting at a particular point in space-time. It's actually moving. So the sun is moving, the Earth, which is orbiting the sun, is also moving translationally, but they're also in the orbit of the sun, right? And then, in fact, if you could look at from another global perspective, the sun is also orbiting some giant star, right? So that's how it really is. Nothing is stationary, nothing is dynamical. Nothing is stationary and nothing is absolute. So everything is relative. So being at Earth, we assume that the sun is stationary. It's not moving. We are revolving around the sun and we are moving. But if an observer who sits outside at some other planet, let's say is very far away at some other star, and he sees our solar system, what he would see is the sun is also moving and the Earth is also moving. But the Earth is in the orbit of the sun. And then the sun is actually orbiting something massive. So it's also orbiting something massive. So that's the idea. And now, Sir Isaac Newton, he gave us this, this expression for the gravitational force. So according to Newton, he said that there is a force which is responsible for the attraction of these two bodies. So Earth is attracted to sun and sun is attracted to the Earth. It's all as well. Why so? Because everything that I said about this mass creating a field in space, this Earth also has some mass. It will also create a field, but the field would be relatively weak compared to the field that was created by the sun. Right? Okay, so that's why Earth would also exert some force on the sun, which is why the sun would be attracted towards the Earth, but the force is so small that it's almost negligible because the Earth mass is so small when it's compared with the mass of the sun. So far, is there any question in anyone's mind? Feel free to ask. By the way, if you're new, I always encourage questions. You should always ask questions. Stop me anywhere in between the lecture. You have any question, fire away. So is there any question so far from anyone? Omar, I know we have went through some of these things already, but let's just take it as it would be a revision for you as well. I hope it's okay for you that we are repeating some of the things.
No issue, sir.
Okay, perfect. So any question so far? Anyone? Hasib, Omar, we also have Fatma Maman, and I think she's also this is her first class, I would assume. So any questions so far?
No, sir, there isn't any question.
Okay, perfect. Right. So, okay, so where was I? Right. So now we can define gravitational field strength at some particular point in space as the gravitational force per unit mass at that point. So I hope this now, this picture that I made this idea pretty clear, because again, it's the same thing that at some point, so where the sun sits at this point, I think I should use different colors now because it's getting, so let's say this is the green point. The sun sits at this point, and now it's going to at this point, this mass of the sun is going to create a gravitational field around that point, right? And any other mass that comes in the vicinity of this field that I'm highlighting as green, any mass that comes in this vicinity would be attracted towards the mass of the sun, or the sun, right? Okay, so that's the idea of a gravitational field, and how strong it is, how strongly it's attracted to the earth is the field, it's the strength of this gravitational field. So hence it's defined at some particular point in space as the gravitational force per unit mass at that point. So with this, we can define this gravitational force. What would be the gravitational force? So experimentally, Newton determined that it should be proportional to the masses. So this capital M is actually the mass of the sun, you can say, or it's the mass of a body which is majorly responsible for the gravitational field. In this case, it's the sun, right? And it's majorly responsible because even Earth is creating gravitational field, but that's pretty small. So sun would not orbit the Earth, but the Earth would orbit the sun. And hence, we denote this capital M as the mass, which is majorly responsible for this field, gravitational field. Or you can say, in other words, or in simpler terms, you can also say it's the mass which has a higher value, right? So a higher mass is denoted with capital M. The force would obviously also be proportional to the mass of this small planet that is there. Because, of course, any planet that would be attracted to this big mass, they both share this gravitational force. So this gravitational force actually comes in pairs. Actually, every force in nature occurs in pairs, right? So this is a pair where you have two bodies that makes a pair, and the gravitational force is between these two bodies. Hence, it's proportional to both of the masses. And then you can experimentally determine that it's inversely proportional to the square of the distance between these two masses, right? So small m and capital M. The distance between these two masses, it's inversely proportional to the square of that. Now, that's also referred to as the inverse square law. Right. Okay, so, but it turns out that there must be a negative sign with this whole thing. And the reason for that negative sign comes from the fact that whenever I have, let me draw something over here. I have this mass. So the radius vector that I'll draw from this mass would be in this outwards direction. It's not a radius vector, actually, it's a position vector, you can say, to some other mass, which is small m. Now, because this r is a position vector, it's a vector, right? So the direction will play a part in defining the physics of this quantity. Now, gravitational force is an attractive force, right? We all know that, we're familiar with that. And so the gravitational force acts in this direction to the center of this capital mass M. So anything that it will basically pull any object towards its center. So there is this difference in these directions, right? So if I'm saying that this direction, let me use a highlighter so I can mark things better. So this direction, if I consider this one as positive, then obviously the direction which is opposite to that will be considered as negative. Hence, if my r is positive, then the force vector should be negative, and hence we have this negative sign with in our expression. So is this a point clear to everyone? Why is there a negative sign in this expression for force? This negative sign appears if you're treating force as a vector, you can also just write its modulus, which would be just the magnitude, and then the negative sign would disappear, right? So you're just concerned with the strength of the force and not the direction of the force. That's when the negative sign is no longer needed. So is there any question so far?
No, sir.
Okay, perfect. So right now we can also have we can also derive the expression, mathematical expression for the field strength, right? So the thing that I was talking about previously, the gravitational field, what would be its strength, right? So how strong of a gravitational field can a mass produce, if you look at this thing, right? So it's very simple, it's very easy, because remember, we know that Newton's laws, which is F equals ma, it's actually, I think it's the Newton's second law, right? Now this thing is applicable to the force of gravity. So the force of gravity, which is G mm by r squared, and then you can also put a negative sign with this to include the direction. In this case, you can see that the small m's just cancel out, and you're left with this thing, right? So the small m's canceled out, and you're left with Gm, capital M by r squared. So that's m. So, and we just call this, instead of calling it A, we rename it to some G, where G, small g, is now defined as the acceleration which occurs due to gravity. So is that clear? This, and then simply this thing, this expression that is highlighted over here is the acceleration due to gravity, right? And you can see that the small mass canceled out, and it should have been canceled out because the gravitational field is being produced by one object, right? So for example, if this is the Earth and this is the this is the sun, and let me just write it in there. So that's the sun, and you have some small mass, let's call it the Earth. The sun creates a gravitational field which is more, you can say, it overcomes the gravitational field that was created by the Earth. So Earth is attracted towards the sun more rather than the sun being attracted towards the Earth. It is attracted towards the Earth, but it's so small that it's almost ignored or negligible. And so that's why the sun basically mainly was majorly responsible for creating this this gravitational field, right? So I'll just draw this line like this. So that's the gravitational field. Sun was majorly responsible for that. So the only bigger mass remains in the expression. And that mass is, as you can see, it's the mass of the object which creates this field G. Next, we have an example, and we are doing this example. It's, we assume that the Earth is a uniform sphere of radius this. So Earth can be assumed as a sphere. The geometry of Earth is a sphere which is constant throughout. So there is no bumps in the sphere. It's a uniform sphere, very smooth. In reality or in practical, that's not really the case, by the way. So that's why we're assuming. And the mass of the Earth is assumed to be this much, 6.0 times 24 kilograms. Find the gravitational field strength G at a point on the surface of the Earth. Now, if you want to find this field strength on the surface of the Earth from the center, it's as far away as the radius of the Earth is, right? So I'll just put in the values. I know G is a constant. Its value is given by 6.67 times 10 raised to power minus 11. That's a constant. We know that. It's also, I think it's given in the formula sheet or a constant sheet for your A-levels exams. Then you have the mass, which would be the mass of the Earth, right? Because what we're doing is we are trying to find out the gravitational field strength at a point on Earth's surface, which is due to the Earth. So we are using the mass of the Earth. And the radius, because we want to find it on the surface, so r, which is the position vector from the center of the Earth to that point where you want the gravitational field strength, that would be then the radius of the Earth, because at the surface, the distance from center to the surface is the radius of the Earth. So we'll just put that value, and it turns out to be 9.77 meters per second squared, right? So which is approximately when equal to the value that you use, 9.81 meters per second squared, right? So the difference in this value is simply because of some of our assumptions of the radius where we rounded these off. These values were given as rounded off. So that's why we got 9.77. Anyways, then you also have next part where it says that at some height, 1.5 times the radius of above the Earth's surface. So you need to find the gravitational field strength, which is, you can say now, this is the surface, and it's 1.5 times the surface, the height at the surface, which is 1.5 times this r. Now, it's very simple. Again, all you have to do is multiply the position vector r, which is 6.4 times 10 raised to power 6 meters, with 1.5. And do everything else would be carried out in the similar fashion. And whatever value you get, it's the value of acceleration of gravity that is above the surface of the Earth. So for example, if you were orbiting the Earth at 1.5 times the radius, then whatever object that is orbiting, it would feel this much of gravity. So what would you expect the answer for this to be, which is 1.5 times above the Earth's surface compared to what we got at the surface? What would you expect the answer to be over here? Higher than this or lower than this? Anyone?
Lower than this.
Yeah, exactly. It would be lower than this. And the reason for that is?
Because the denominator is bigger. And we are getting
yeah, so mathematically,
exactly.
So yeah, both mathematically and physically give the reason. Perfect. So that's correct, right? Because it follows this inverse square relationship. So the field strength would decrease as the radius or the position vector increases. Perfect. Right. So then we have another example, which says that the acceleration due to gravity at the Earth's surface is 9.8 meters per second squared. We are aware of that. Calculate the acceleration due to gravity on the planet, which has same density, but twice the radius of the Earth. So apparently there is some other planet, right? So this is Earth, and there is another planet. It has the density of this planet, P, is the same as the density of Earth, but the radius is 2 times the radius of the Earth. So how can you go about this problem? Remember, we need to calculate the acceleration due to gravity. So we write down this expression for acceleration due to gravity, which we know, which is this thing. And these are our values that we know, that the gravity on Earth is 9.8. The densities are the same. So we'll just call it some constant rho. And the radius of this planet is 2 times the radius of the Earth. You'll just put these values in this ratio. You'll write down the planet's gravity, and you'll divide that by the Earth's gravity. And the reason we're doing that is because we want something that gives you RP over RE, this type of thing. And if I have this thing, then I can replace it with 2, right? So this thing is basically 2. And then we can write it down in terms of the Earth, the acceleration due to gravity, which would be because well, everything is really a constant in this case. You can see that, see, in this GP, this G is constant. We can write down, by the way, here's one thing, that you can write down the mass in terms of the density simply by using this relation. Density is mass by volume, where mass would be density times volume. And in place of the volume, they have told you that it's assumed to be a uniform sphere. So we know the volume of a sphere is 4/3 pi r cube. So we'll just replace this, and we'd have this thing in this upper, you call it numerator, right? Numerator, and then for the Earth, we had put some values for in the denominator. Similarly, G and G are constants. Rho is the same for both, so that is constant as well. Cancel out. 4/3. 4/3 is a constant. Pi is a constant. Cancels out. And from this part, you see that when you divide this with the radius of the planet r squared, which is from this thing, and upstairs you have this r cube that comes from the volume. So it cancels out and you're left with 1 rp over here. And similarly, in this expression, the same thing happens with re. So you're left with rp over re. Now you can simply just replace this thing with 2. And then the acceleration due to gravity on planet is 2 times the acceleration due to gravity on the Earth. So you just multiply 2 with 9.8, and that's this thing. Is this clear, or should I just explain? I've explained this in the previous lecture, which you can find on YouTube. So I went kind of quickly. I tried to go a bit quickly, but I think, did I get the point across? Is it clear?
Yes,
What
sir.
we did? Okay,
Yes, sir.
so if it's not, you can also go and watch the video on YouTube for this lecture. And if it's still not clear, feel free to ask me again. You can ask it on in the WhatsApp group. You can message me on WhatsApp as well, and you can even ask in the next class, right? Okay, so we'll move forward now. And so the thing is done over here again in a much more neater way, you can say. So, okay, now the next thing is that everything that is written over here is something that I have already explained to you. How do we find this relation for acceleration due to gravity? And it's done by using the force of gravity is equal to the mass times acceleration. And then you can just cancel things out and you get this thing. This is clear, right? I just did this same thing over here. This one.
Clear, sir.
Right, perfect. So then let's do another example. And that says that you have a ship which is at rest on the Earth's equator. So here's this Earth, and this is the equator of the Earth, right? It's the center line. And you have a ship which is stationary over here. Assume that the Earth is a perfect sphere of radius r and acceleration due to gravity. At the poles is g0, right? This g with subscript 0. So at this poles, we have g0. That's the acceleration due to gravity. Are you aware of the fact that the acceleration due to gravity would be different at the poles compared to at the equator? Does everyone understand why would that be? Because the gravity acceleration due to gravity is towards the center, right? So the equator is actually nearer to the center compared to the poles, which are further from the center. So the radius vector for the poles would be higher compared to the radius vector of the equator. So that's clear?
Yes, sir.
Okay, so that's the reason they gave you this at the poles, it's some G naught, right? Express its apparent weight N of a body mass M in terms of M, G naught, R, and T. T is the time period of the Earth. That is just the period where Earth performs one complete orbit around the sun, right? So that's, and we know that's just, sorry, around, not around the sun. I'm sorry. It performs this, it rotates with some angular velocity omega about its axis, right? And in reality, this axis, all of this thing, it's slightly tilted. Can I tilt it using this tool? I cannot, but it's kind of tilted, right? And so it performs this rotation, and the time period is defined as the Earth, for Earth to perform this one complete revolution, which is your 1 day, 24 hours, right? Okay, so that's what we have to do now. Okay, so we know that at the pole we can write down an expression for force, and then we can write down an expression for force at the equator as well. Now, for the ship to be the ship is at rest on the Earth's equator, so there is no dynamics really happening, right? So the ship is at rest. So the force expression for force will simply be Gm me times m over r squared, where this me is the mass of the Earth, small m is the mass of the ship, and this r squared is the, you should give it some subscript p, which is the radius at the pole. Now this would be equal to m times a, but because a is simply acceleration due to gravity, we called it g. And instead of writing g, I wrote g naught, because this is happening at the poles, and at poles we are given that the gravity is g naught. Similarly, you can do the same thing at the equator. Now at the equator, if you look at this diagram, you have some normal force because the ship lies on the surface, right? Like this, it's on the surface. And so there is some normal force from the Earth, and there is some weight of this ship